Hi there. Welcome to Xamarin University. My name is Mark Smith, and we're going to talk about cleaning up non-memory resources. Now, this class is an extension of CSC270, and so I kind of expect that you've already seen that, or at least you're familiar with the fundamentals of garbage collection. Because what we're going to talk about here is cleaning up things that aren't memory-related resources. So it turns out our applications are really good at cleaning up memory simply because they have a garbage collector that comes along behind us and makes sure to clean up anything that we're not using anymore. But applications work with a variety of other types of resources, such as files and database files, network streams, and even other sorts of bits of information that we might be needing from the native operating system, such as UI widgets, buttons, and things like that. But we have to keep in mind that really the garbage collector is only interested and only knows about memory. And so how do we clean up these other types of resources? For example, if I have a file that I open with a stream reader, and I read the contents of this file and I return them back from this function, when is the file actually closed? Now, we know that the file is going to be opened as part of the constructor of the stream reader where I pass in the file name, or perhaps it's opened the minute I call some API to actually read the file, such as here we're calling read to end. But when is the file actually going to get closed? Because presumably I could change the stream's position and then begin rereading portions of it. Or perhaps is it closed as soon as we're done reading to the end? Well, let's actually check this and find out. So here I am in Visual Studio, and I have a little Xamarin Forms application here with Android, iOS, and UWP versions, and all three will exhibit the exact same issues. So I'm opening a file with a file stream. You can see I'm randomly reaching into that file and picking one of the lines out of it, and I'm going to display it as a joke of the day. So if I run this, and notice that we're not closing the file or doing anything strange with it, we're just creating the file stream inside this handler, and each time we hit that handler, we're going to create that same file stream. So I'm going to hit the Tell Me a Joke button, which will activate this bit of code here. And notice I get my joke of the day. Can a kangaroo jump higher than a house? Of course, a house doesn't jump at all. I click OK, and I click it again to give me another one. And notice the second time I get error reading file sharing violation on path data, closing handles, droid, files, jokes, text, because I'm unable to open this file. And the reason I'm unable to open the file is because the previous file stream already opened this file. And so it's a sharing violation, and I can keep pressing this button, but I'm going to get essentially the same result each time. And notice this time, I get joke of the day again. Daddy, did you know that girls are smarter than boys? No, I didn't know that. There you go. And so I'm going to click OK again, and notice now the third time, I'm going to get that same sharing violation. But something happened that time that allowed me to read the file. That something is a garbage collection kicked in. And as a result of that GC, the file got closed. Now let's just verify that. Let's go ahead and add another button in here. So I'm going to copy this button. And let's just make this one green. And we'll call a method on doGC. Then let's set the text to be doGC. Text color's white is fine. Let's go ahead and add our method. And I'm just going to do a GC collect. Let's run it again and see if that fixes our problem. So we'll say, tell me a joke. I get my joke. What is green and sits crying in the corner? The Incredible Sulk. I do a GC, tell me a joke, and notice that I get my joke again. I'm sorry you suffer from a terminal illness and have only 10 to live. What do you mean 10? 10 what? Months? Weeks? Doctor. 9. Hit tell me a joke. Notice I get my sharing violation, but I do a GC, tell me a joke, and now I get my joke again. So it is clearly the GC somehow that's causing that file stream to get closed. But we don't want to wait for a GC, and we certainly don't want to have to do a GC collect every single time. So let's go back and talk about some of the other things that we can do to try to make sure that this file gets closed in a timely fashion. So you saw that we actually need a garbage collection to kick in to actually free the file, to get rid of the file handle and make sure that it gets closed. And this particular problem is something that's intrinsic to most garbage collected systems. And the issue really is we can't count on the garbage collection being deterministic about closing resources. And so you saw in the case of that demonstration where I can't reopen the file a second time because the file handle is still open for some period of time until a garbage collect occurs. That's the reason why Microsoft created the iDisposable interface that you see here. The idea behind iDisposable is to give the client application an opportunity to indicate that they're finished with this resource and that we should go ahead and get rid of it. Now, I want to be clear here. This simply indicates that we're done with the resource. It has nothing to do with garbage collection itself. So implementing iDisposable doesn't impact how the garbage collector works or even when the garbage collector would see your object. But what it does do is allow us to do some of that critical freeing of resources, in other words, closing that file handle that's important to us prior to the garbage collection kicking in. And so the way that we do that is through this iDisposable interface. So notice that it has a single method, dispose, on the interface itself, and the goal is really, as a client, to call dispose when we're finished using the resource. And so here you have our read.json data method again. And notice, again, we're going to go ahead and allocate the stream reader, and this time we're going to surround the read to end and try finally. And in the finally, I'm going to actually use the dispose method on stream reader because it turns out that stream reader implements iDisposable. And so when we hit our finally block, we'll close that file handle, and then at some point in the future, just like it did before, the GC will kick in and it will actually free the memory that's behind the stream reader. But it won't have to close the file anymore because we'll already have done that with the iDisposable interface. Now, there's actually a second way you can do this, and that is using the using keyword. And so fairly late in the C# language definition, prior to its final release of 1.0, Microsoft created or reused the using keyword in a different context. And so the statement that you put inside the using block itself, this right here that you can see, so this stream reader, reader equal new stream reader file name, this portion of the block has to be something that's disposable. And if it is, then the using statement will generate the code that we saw earlier, just like this, where we actually have a finally, where we actually do the dispose. That's done automatically by the C# compiler, and so this is a very common way of invoking the dispose method on iDisposable objects. The key takeaway here is that it's your code that has to call dispose, regardless of whether you do it in a finally block or whether you use a using construct or whether you just call the method. It has to be some piece of user code that actually invokes this method. The runtime does not call dispose for you. The GC does not call dispose for you. It's your responsibility. Now, a lot of things have or implement iDisposable capabilities. And so if you look at most of the native platform functions, and this is going to be true on iOS, Android, or Windows, you'll find that a lot of types implement iDisposable because they're native types. And so they represent something that's actually intrinsic to the platform, and it probably holds on to some kind of native resource handle that we want to make sure to get rid of. And so here in this particular case, notice that we have iOS. The NS object type is the base object type for almost everything that you interact with. And so this includes view controllers and views and all the other little UI widgets that you might play with. And notice that they're all iDisposable. What that means is that we can then call dispose on them when we're finished. And actually this is a good idea in order to keep our memory requirements down because this allows us to clean up the native side of the resource. So for example, here's a little bit of code. Notice in our view did appear, again this is Xamarin iOS, we're using NS Notification Center. And we're retrieving the default notification center and we're calling add observer on one of the keys. Now what this will do is this will essentially connect a delegate up for us so that we can get notified on things like our orientation changing or perhaps the battery status changing. And notice that the method returns a token of type NSObject. Now you just saw that NSObject implements iDisposable. And so what we can do is when we're ready to get rid of this particular notification, I could call remove observer and pass in that token. But for simplicity purposes, I can also simply call dispose on that NS token, and it will automatically unregister. You'll see this sort of behavior in a lot of different places. Dispose will be exposed on a type, either to clean that type up or to provide some way to disconnect from that type, like you see here with NS Notification Center. So let's take a look at using iDisposable, particularly with our file example that we saw just a moment ago. So here we are back in our application, and if you recall, our problem is the file stream itself isn't getting closed, and we have a couple of different ways we could fix this. It turns out there actually is, on the file stream, a close method. And I could call this to actually close the file. I can also do it on the stream reader. So notice both of these have a close method. However, they both also implement iDisposable. And I can dispose either one. And this is kind of interesting because the stream reader itself actually takes ownership of the stream that you pass in. There's an optional constructor parameter that lets you control that. So you can actually pass in a parameter that indicates that you don't want the stream reader to own the stream, and instead what will happen is then it won't close or dispose the stream when you call close on the stream reader itself. And so we can actually fix our problem by disposing either one of these objects. And so just to show that, let's put a using statement onto the stream reader. And then after we've read our line, we'll go ahead and do a dispose of stream reader. Remember, using just turns into try finally. So to verify this, let's go ahead and run it. And what should happen is now every time I click the tell me a joke button, I should see a new joke. So I should not need to do a GC anymore. Instead, notice I say tell me a joke and it gives me a joke. Tell me a joke, I get another joke. Tell me a joke, I get another joke. And so each time I'm closing that stream. And again, I could do it with either one of these. And so we could put that same using onto the file stream. In fact, we could do it to both. It would be fine because dispose is simply going to be called on both of those objects. And it would just ensure the stream is closed. And so if the stream is already closed, then dispose won't do anything. And so we've successfully fixed our problem that we had with the stream reader. So we can, in recap, either close the stream directly through the call to close through either object, or we can dispose of either object. Both will have the same effect. So sometimes it's useful for us to implement iDisposable as well. And really there's two times that you're going to want to make sure to do this in your class. So if your class either A, creates and owns its own native resources, in other words, you're holding on to an operating system handle through some native API that you've invoked through some sort of pinvoke layer, then you need to go ahead and implement iDisposable. Or B, if you're holding on to reference types that in themselves implement iDisposable. So for example, if I had a class that was using a stream reader, then I would want to go ahead and implement iDisposable myself so that I could then in turn dispose that stream reader when my client disposes me. So the key thing is that the dispose method has to make sure to release all of the held resources. That means that if you're holding on to a native handle, then you'll want to go ahead and invoke the native API to release that handle. Or if you're holding on to a managed type that implements iDisposable, you're going to want to go ahead and call dispose on that managed type. Now, keep in mind that you only want to do this if you own the type. In other words, if you're past a stream reader and you're not the owner of that stream reader, something else is going to control its lifetime, then you don't want to dispose it because you want to allow the owner of that type to dispose it. But if you're the owner, like you see here in our data loader class, where the stream reader is an internal implementation detail that we're not exposing to the client, in other words, we're using it inside of our class, then we want to make sure to go ahead and dispose it when we're finished with it. And in this particular case, we can't use using because we don't know the lifetime. The client's going to decide the lifetime of my data loader, and that in turn decides the lifetime of the stream reader. And so notice that we're going to implement iDisposable, and in our dispose method, we call the dispose method of the stream reader itself, thus forwarding the call and cleaning up those resources. Now, there's some rules that we have to follow when we implement iDisposable. The first thing is that dispose should never throw an exception. Now, I'm going to provide a slight caveat to this, and that is if the type that you're trying to dispose fails and you get some kind of critical failure that destabilizes your application in some way, in other words, it makes the runtime unavailable or holds a whole bunch of stuff that we simply can't run anymore, then in that case, it is legal to throw an exception. But generally speaking, you don't want to have exceptions flow outside your dispose because almost no code out there that uses iDisposable will actually wrap it in a try-catch. And in fact, if you use the using statement, it's always a try finally, not a try-catch. And so exceptions will almost always terminate your process. The second rule is, once we've called dispose in the object, we should consider that object dead. In other words, we shouldn't allow any other method or property to work correctly on that object once dispose has been called. The way that you can do this is Microsoft provided a built-in exception type called object disposed exception, and you can throw this from any of your methods and properties once your object's been disposed to indicate that this object is no longer valid. The third rule is dispose should always be idempotent. Now what I mean by that is if you call dispose multiple times, then the second and subsequent time it should simply return. It should do the disposal the first time, but subsequent requests to dispose the object should not fail and should not throw an exception. And so it should just return directly from the call. This is why it's acceptable to dispose both the file stream and the stream reader without any ill effect. The very first one will actually close and dispose the file, and the second call wouldn't do anything because the underlying object has already been closed. So let's revisit our implementation of iDisposable. Here we've got our data loader. Remember, it has a stream reader. We're now going to track whether or not we've disposed this object. So notice in our dispose method, we're going to look at a Boolean flag and say, if we've not been disposed yet, then let's go ahead and dispose the stream reader. Notice that I'm making sure that it doesn't throw an exception if it's null. So if we didn't actually get to the point where we allocated the stream reader, in other words, whatever method does the allocation of stream reader, maybe it wasn't ever called, but we still dispose this, I want to make sure if it's null that we don't throw a null reference exception. And so we're using the null operator there to make sure that that doesn't happen. We're calling dispose on the reader, and then we're setting our disposed flag to true. Then notice in our read JSON data, if the disposed flag is true, we throw a new object disposed exception. This then follows all three of the rules that we just pointed out. We're not allowing exceptions to bubble out of the disposed type. We're making sure that you can't call the read JSON data after the object's been disposed, and subsequent calls to dispose will simply return without any ill effect. Now this brings up an interesting thing, which is, what about close methods? A lot of people confuse whether or not to call close or dispose, and often they'll do very similar, if not exactly the same thing. So if your particular platform thing that you're working with has the idea of being able to close itself, in other words, the semantics for the type allow for an open-close kind of language, then you should go ahead and implement a close method on the type as well. So this includes things like database connections and network streams, which have sort of an open-close sort of paradigm to them. You should also implement iDisposable because it'll allow us to use nice semantics such as the using keyword to be able to get rid of the type pretty easily. And most of the time, your close and your dispose will do the same thing. The only exception will be if the type that you're working with can be reopened after you've used it, then close should allow for that sort of behavior. In other words, closing the type would allow me to then call open again on the same exact instance and allow the object to work, whereas dispose should actually shut the type down completely. You should not be able to reopen the object after you've disposed it. And so in that case, there's a subtle distinction between calling close to get rid of the resource versus dispose, which actually makes the resource unavailable after that point. Now, the other thing where iDisposable gets a little bit interesting is where we involve inheritance. And so in this particular case, notice that I have a base class which implements iDisposable, and therefore I've defined my public void dispose method. And I now have a derived class that derives from base class, and it also wants to be disposable. Now the issue with this is my base class already declared the iDisposable interface, and it's public, but it's not virtual, so I can't override it. But we can do a little bit of a trick, which is we can re-implement iDisposable on the derived type. This is called explicit interface inheritance. So notice that we've implemented iDisposable on my derived class, and I'm using this void iDisposable.dispose sort of implementation here, where I put the type name with a dot and then put the dispose method. This is the explicit interface implementation. Now, what's going to happen here is the system will then re-implement iDisposable, and when I call my derived class dispose, I'll get dispose, and then I can call the base class dispose method, and it will pass along to the base. And this all generally will work properly, except in one particular case, which is if I actually cast my derived class to the base class, and now I'm using my base class reference, and I call dispose, I'm not going to end up in my derived class dispose implementation. Instead, it will simply call the base class dispose implementation. And in fact, it gets even weirder because if I cast that base class to iDisposable, then I will properly go through the derived class. And so what that means is if you use the using construct, then this will work just fine because it always casts to iDisposable first. This is a very tricky problem because it can have insidious consequences, and it's also kind of hard to track down. In fact, even Microsoft has made this mistake in the framework. If you go look at the ping class out of the system components namespace, they actually had a ping component that would let you do like an ICMP request, and if you disposed it as a network object, then it would go through the base implementation, but if you disposed it as the ping object, then it would actually dispose the ping itself. And so it didn't work depending on how you were actually using that particular object. And so it's kind of interesting because even Microsoft has fallen into this exact problem. So how do we solve this? Well, Microsoft solved it by implementing what they call the dispose pattern. So this is a little different than just iDisposable itself. It actually is a guideline for how to provide disposal sort of semantics for your objects. And the idea is that we not only implement iDisposable with the public void dispose method, but we also provide a protected virtual implementation called Dispose, so the same method name, but one that takes a parameter, which is a Boolean. The Boolean indicates if we're being called from the dispose method. And so notice here that when we implement public void dispose, we call the dispose method with the Boolean value of true. We then look to say, have we been disposed? And then if we're disposing, in other words, we're being called from the dispose method, then we go ahead and dispose our reader and we set the dispose flag to true. So the idea is in our actual virtual dispose method, we do all of our cleanup. And the implementation of iDisposable dispose simply forwards to that virtual method. So how does this impact our inheritance model? Well, it means that when we derive from this data loader, I simply have to override that dispose method because it's protected and it's virtual. I can provide my own override here, and that way I guarantee that no matter which way I call this object, as a base data loader, as iDisposable, or as second data loader, I will always come through this logic because it's always going to come through that virtual method. And so we want to make sure to implement this style or this pattern of disposable whenever we're working with our objects and creating an inheritance graph so that we guarantee that disposal always works. In fact, I'm even going to say that if you anticipate that you might need a disposable sort of interface at any point in the future, even if you're not doing it today, and your class is not sealed, then you should go ahead and implement the disposable pattern right up front. Because trying to bake it in after the fact, after other clients are deriving from you or potentially deriving from you, is going to be a nightmare because it's going to be a breaking contract change in your types. This isn't as bad in the mobile world where we kind of have to ship all of our types with our application, but in the desktop world where potentially that type is in a DLL that's perhaps in the global assembly cache, or maybe it's a shared component, this can be disastrous because it can break all kinds of things. And so if you think that your object's going to need dispose, then you should go ahead and implement the disposable pattern up front. Now there are some issues with iDisposable. It's not quite as hunky-dory as it seems, because the idea was that iDisposable was created really to solve the issue of releasing resources in a deterministic fashion. In other words, we don't want to rely on the garbage collector to do the release of those files. We want to make sure that they go away a little bit quicker. But as you've seen, dispose isn't actually called by the runtime. In fact, there's nothing in the runtime that will do a dispose on your types. It relies completely on your code calling dispose. So your client code, whoever's using the type that is disposable, has to actually manage this particular call. And they have to actually put a direct call to the dispose method in order to get rid of the resources. So what happens if you don't call dispose? Well, we know that it actually does get cleaned up eventually by the GC. And the thing that's doing that is something called a finalizer. A finalizer is a portion of the garbage collection system that does a last chance check to say, hey, you're about to be freed up, your memory's about to go away, and your object state is going to be destroyed. Do you have something that needs to be cleaned up before that happens? And so the idea is, here we've got a couple of object graphs. We've got a GC that's occurring, and we have the reachable live objects. Those are the things that are going to get promoted to the next generation potentially, but things that are going to stay alive. And then we have the gray unreachable dead objects. And in this case, one of these objects in the unreachable area needs to do some additional cleanup. It's a file stream, and it needs to close that file handle. It's going to be able to close that by creating a finalizer on the type. Now, there is a cost to this. So finalizers actually are fairly significant in a couple of ways. First, when we allocate a finalizable type, in this case F, the first thing that needs to happen is the system recognizes that it has a finalizer and it adds it to a special queue called the registered for finalization queue. And by the way, these details are true of both .NET and of Mono, so the sgen collector does exactly the same thing. So we add this type into a special queue. Now, at some point, the GC is going to kick in, and every time GC runs in your application, it has to look at this queue to say, are there objects that are no longer reachable from user code, but still have a reference in the registered for finalization queue? And so every GC gets impacted by us having a finalizer on our type. Now, at some point, the GC will kick in, and it will look at that queue, and it'll say, I see I have this F object, and this F object is not reachable by user code, but it's in the registered for finalization queue. So it will pull it out of that registered for finalization queue. It will promote the F object to the next generation. So if it was in the nursery, it moves to the major generation, and it will put it in a new queue called the ready to finalize queue. Now this is a special queue because the minute we put something in here, the garbage collector is going to keep on going and start collecting other stuff, and at some point it will finish and our application will start running again. And another thread gets woken up because there was something added into this queue. This is the dedicated finalizer thread. This is a high priority system thread that was created specifically to do finalization. There's just one of them, and it finalizes all the objects that are in the ready to finalize queue. The way it does that is it calls a virtual method on the object called finalize. And it goes ahead and calls the finalize method one at a time for every single object that was in the queue, and once it returns, then the finalizer is finished and it goes back to sleep. The way this looks in terms of a visual representation is, notice that here we've got some objects, E, F, G, H, and J. All of these are on the major heap because they all got promoted, and F had a finalizer, so we have to keep it alive at least long enough for the finalizer thread to run. So it automatically gets promoted, and now we have to wait for the next major collection before F can actually go away. Now keep in mind that the finalizer will have run, and so we'll have cleaned up native resources, we'll have thrown away file handles and closed them and things like that, but the memory space that was occupied by F cannot be freed until the next major collection of the GC. And so we make sure that it stays around long enough to get the finalizer called, and then the next major GC that happens is when this gets cleaned up. Now what that means to you is that your objects that are finalized, or I should say finalizable objects, always live much, much longer than normal. And so normally we would get rid of these fairly early on, but because it has a finalizer, it has to live long enough to get that finalizer to get called, and because it's a different thread and it's run in parallel potentially to the rest of your app, therefore this is something that has to live longer than normal. And it always gets cleaned up on the next GC collection. So how do we declare a finalizer? Well, it's done through a language-specific syntax. In this particular case, in C# we use the tilde class name syntax. And so it looks kind of like a C++ destructor, but it's not a destructor because it's not deterministic. And so notice here we've got our F, and we have tilde F that indicates our finalizer. So notice it doesn't have any sort of visibility modifier. We don't say public or private or protected or internal or anything like that, because this is a special syntax that generates a method for us that ensures that the finalizer is only called by the runtime. So you should never invoke this method yourself. Instead, you should always let the finalizer thread do that. Now, the way that this works, if we actually use this tilde class name syntax, ultimately what gets generated by the compiler is some code that looks like this. So again, remember we had code like this where we used tilde F and we had no constructor, but when the compiler actually generates the class, it's going to have a public default constructor that gets generated by the compiler. So remember that always happens if you don't declare one, unless you have a customized constructor. So if you have a non-default constructor, then it won't generate one for you. But the fact that we didn't have a constructor caused us to create one. Then it creates an override for the protected void finalize method. And this is where it drops all the code that you place inside the tilde class name method. And so this code would then be executed by the finalizer when it runs. So let's just look at that. Let's go ahead and create a finalizer and just see in real time what sort of cost it has. So to see the cost of a finalizer, let's use an iOS project. And so I created a Xamarin Forms project here that has a button and a label in it. And in the button handler, we're going to allocate a set of objects. And to start out with, I just want to know what the cost is to just allocate normal objects. And so let's just create a public class, we'll call it dummy, that really doesn't have anything in it. Let's just put an int value in there. So it just has a field. And then let's go into a loop and let's time how long it takes to create 1,000,000 of these. So first let's create a stopwatch. So we'll create a new stopwatch and then let's go into a loop. Let's do it for 1,000,000 times. And then inside here, let's just create a dummy. And then I want to know how long it takes, and so we'll do a stop. And let's output that to our label. So our label right now is called total time label. So let's say total time label text is equal to elapsed. And that'll be the output from the timer. We have to do a toString on that. And this wants it to put it into an assignment. So let's just say var d equal new dummy. So we aren't going to do anything with it. We'll let it get collected right away. That's fine. But I want to know how long this takes. So let's run this. And we'll just run it in the simulator, recognizing that the simulator is going to be really fast. But because we'll run all the tests in the simulator, it'll be okay. We're just comparing times to each other, not to absolute time. So our app comes up. We're going to create 1,000,000 objects. And notice it takes 0.027 milliseconds. 0.027 milliseconds. It's very fast, right? We just created 1,000,000 objects. That's pretty awesome. Now let's see what happens if I put a finalizer on this. So I'm just going to say finalizer, and I'm not even going to have the finalizer do anything, right? It'll just be an empty finalizer that'll be part of the dummy class. Let's try it again. So again, I'm going to create a million objects, and notice now my time is 0.52 milliseconds. Before it was 0.02, and it went to 0.52. Now, that encompasses both the time it takes to finalize the object as well as the creation of the object itself. So let's try to minimize some of that. Let's go ahead and say after we allocate the object, let's say GC suppress finalize. And let's suppress the finalizer for this object. In other words, we don't want the finalizer to run. And let's just see what the allocation cost is for this object. So it was 0.5 versus 0.02. Run it one more time, and now notice it's 0.356. And so even the allocation of the object is expensive when we have a finalizer. So just be aware of that. There is an expense to this. These can be very useful in certain situations. And in fact, in XAM370, we'll talk about some diagnostic situations that you can use finalizers in. But they do come at a cost. Now, finalizers actually affect the dispose pattern. So remember, we had this dispose pattern that we used where we had a virtual method called dispose that takes a Boolean. And you might be asking, why in the world did we pass this Boolean? Because it seemed like the only time that we did anything with it was when we call dispose, we pass in true. Well, the pattern was designed from the very beginning to take into account finalizers. And so, in fact, when we add a finalizer into our type, we're also going to call that same dispose override, but instead of passing true, we're going to pass false. This indicates that we're cleaning up native resources. This is coming from the finalizer, and therefore I want to do all the native resource cleanup that's going to occur from finalization. And so here we pass in false, but again, all of our code is going to actually clean up inside that dispose method. So here's just an example of the dispose method. So notice here we're going to say if the object hasn't been disposed, so we're going to check our dispose flag, and if we're disposing, then this is being called from the dispose method, and I want to clean up all my managed resources. These are objects such as my stream reader that I want to call dispose on. So things that are managed that implement Disposable, I'm going to do those only in response to a call from the dispose method. That's important, and you'll see why in just a moment. Then, once we have done that, we'll clean up our native resources, and if we're called from a finalizer, in other words, we're passing in false for our isDisposing flag, then I only want to clean up the native resources. So specifically, the handles that I may have allocated from the operating system. I don't want to do any sort of managed cleanup in here because the managed resources may not be available. So let me show you what I mean by that. So here I've got my class F that implements iDisposable, and notice that it allocates a class G that is also iDisposable, and both of these have finalizers. Now, in my finalizer for F, notice that I'm calling g.toString. Now here's the issue. When finalizers run, there's no guaranteed order to them. So in this particular case, I've got F and G, both have a finalizer, both would be put in the ready to finalize queue, and the finalizer thread will wake up and it'll pull one of them out of that queue, and the order that they were put in that queue is going to be based strictly on the order that the GC system happened to see them in the original queue. So what that means is G could have already been finalized. And so when I try to call g.toString, the state of that object is now unknown because potentially it's already been finalized. So here's just sort of a quick sort of picture of it. So we've got a finalizer thread, and if F gets finalized followed by G, then it would be okay for F to call toString on G. But if G gets finalized first and then we call F, then we don't really know what's going to happen because we don't know what the toString implementation of G does. If it uses some of those handles that potentially got allocated, then it's going to be a big problem for us. So the bottom line is you should never touch or rely on managed state inside your finalizers. Instead, you should only free native operating system resources. Now, when you are doing a dispose, so when we pass in true for our dispose flag, one of the things that we don't need to have happen anymore is we don't need a finalizer to run. So if we've called dispose, the idea behind dispose is I want to clean up my native resources and any of my managed resources. So if I have called dispose, then there's no need for the finalizer to come along after that and clean up the native things because I'll have already done it as part of my dispose. So notice dispose cleans up both the managed and the native resources. So there's no need for a finalizer. Now the way that we stop the finalizer from running on our object is we call gc suppress finalize. This effectively removes it from the finalization queue. And so remember, there was that initial queue that we have that the object got placed in as part of the allocation. The GC suppress finalize takes it out of that queue so that when the GC runs, it won't be in the queue, and therefore this object can go away sooner than before. In the same way, we should consider a finalizer to be a potential error in our application. So if we've implemented Disposable, which we should, and we don't call Dispose on the object, then we want to consider that to be a fatal error of using our object, and we want to report that back to the client. And so in this case, we're going to go ahead and add a debug assert into our Dispose implementation to say, hey, this object has a finalizer, which is expensive, and it implements Disposable to get rid of those resources in a more timely deterministic fashion, and you didn't call Dispose. This will then throw up a message box, and it will tell the user, hey, this name of F, that means just F, was not disposed properly, and we're going to just use the debug assert off of the is disposing flag. So if the flag comes in as false, then it means we were called from the finalizer, and therefore this is considered an error. But it's only an error in debug builds. We obviously don't want this to happen in release builds. We don't want debug things to happen there. But this is more of a diagnostic to indicate we have an issue in our application. There's something that our client that's using the F object is not doing correctly with our object. Now, there's a couple of issues that you're going to run into with finalizers. One is you have to keep in mind that when you execute finalizers, it always executes client code. In other words, you're running code that you write as a programmer as part of a system thread, the finalization thread. If, for instance, I somehow end up in some sort of loop, an infinite loop in this case, while true, or worse, perhaps I block in some way. I make some API that makes a call to something that is a blocking call on the finalizer thread, then I will block the finalizer, and therefore all the objects that are in the finalization queue will never get collected. They will sit in that queue forever from that point forward. There's only one finalizer thread. And if you impact its ability to finalize objects, then ultimately you're impacting the performance and the memory usage of your application, because you're going to end up with a memory leak. The second thing that's kind of interesting that you can do is, notice here I've got my F class, and in my finalizer, I'm actually going to take my this reference, and I'm going to put it back onto a public static. Now remember, statics are live roots. In other words, anything that points at by a static is always considered reachable by my code, and therefore what's really happening here is I'm resurrecting this object. Now this actually can be beneficial. It's not a good idea necessarily to resurrect objects, but I've seen people do it for good reasons. Generally speaking, you shouldn't do this, but it is a perfectly valid scenario to use. In this case, not so much, because I'm simply making it alive, but there are times that you do want to do this, and there's a couple of caveats to it. So the first thing that you want to remember is, once we finalize the object, it's now out of that ready to finalize queue, and therefore, even though I made it alive again, it's not going to get finalized a second time. It doesn't get put back into the needs finalization queue. All right. So once it's out of that queue, it's out for good. So one of the first things you need to know is, how do we re-register this for finalization? Well, we do that by adding a call to gc re-register for finalize. And we pass in our this reference, and this will put it back into that finalization queue to say, hey, when this object no longer has reachable references, let's make sure that it gets finalized. So notice this code here. This is kind of interesting. Say, for instance, that we had some kind of expensive object, and we don't necessarily want to throw these objects away. We want to allocate and reuse them in kind of a pool sort of fashion. So I can have a static create function that will either get one from our private, well, in this case, a public list of pool objects, or it will allocate a new one. And when the object is no longer reachable, so our user code has gotten rid of it, and it gets finalized, then the finalizer gets called, and notice what it's doing is it's putting the object back into the pool. This makes it alive again, and it makes it available for us to use with the next call to create. So this is a way of just sort of reusing these objects. Now, you might look at this and go, hey, that's really cool. That's a great idea. And generally speaking, it's not a terrible idea. You can do this. The problem is you have to remember that the GC semantics and the finalizers are not deterministic. So we don't really know when this object will get put back in the pool, or if even it will get put back in the pool, because it's possible that, you know, we don't run any more GCs. We end up in a tight loop that's not doing a whole lot of memory allocations, and therefore our GCs just aren't happening as frequently, and therefore these objects aren't put back in the pool. it's not a great idea just from the perspective that it's difficult to determine when the objects would be repooled, so to speak, because we don't know when the finalizer is going to run. But this is a valid scenario where potentially you could use this resurrection capability to your benefit. Now, there's often some confusion about when to use finalizers versus iDisposable. So here's the basic rule. If you have an object that holds on to a native operating system handle, in other words, something that you've retrieved with pinvoke, that you're going into the native OS and you're getting back a native resource from it, then you should always have a finalizer. So you should always implement finalize, and you should always have iDisposable. So if it has a finalizer, then you should always have iDisposable to get rid of it in a more timely fashion. Now, if you've got resources that in turn implement iDisposable, then you should implement iDisposable, but you do not need a finalizer. Finalizers are only for native operating system things. You do not need one if the objects that you're holding onto are strictly managed, even if those managed types in themselves hold on to native things. So in the case of a file stream, for example, it clearly is holding on to a native file handle, but my client object using the file stream does not need to implement a finalizer. I would simply implement iDisposable if I'm wrapping that file stream in order to dispose the file stream. The file stream is the thing that would have the finalizer. Okay, so it's only the direct owner of the native resource that implements finalize. Anything else is strictly iDisposable. So what does that mean? Well, again, the purpose of finalizers was to get rid of native things. And the reality is there are very few types today in any of the platforms that are not already wrapped by some managed API. And so it's fairly rare now to actually need a finalizer. Now in XAM370, you'll see a usage of finalizers for diagnostic purposes, so to tell when an object's being cleaned up to kind of detect memory leaks. But generally speaking, that wasn't the intent of the finalizer. The finalizer was to ensure that we didn't have a native resource leak for those objects that were holding on to native file handles and network streams and things like that. And as you've seen, finalizers are kind of tricky to put together, right? So sometimes it's kind of tricky to use the disposable pattern and to kind of make sure that everything's being cleaned up properly and to know whether or not this is managed or native. And as a result, in .NET 2, Microsoft actually implemented a different type of finalizer called a critical finalizer to ensure that A, things got cleaned up a little more appropriately, and B, to make it easier to actually kind of manage this sort of finalization process. And they exposed it through something called a safe handle. The safe handle was introduced to essentially always ensure that native OS handles were released properly and in a timely fashion. And they do it without the use of the owner itself implementing a finalizer. In other words, the client that owns the handle no longer needs to implement a finalizer. They simply own a safe handle, and the safe handle is then used to access that native operating system handle. And so the pattern is that the file stream object implements iDisposable, and it holds a safe handle, and the safe handle is what actually does the cleaning of the resources. And so this is a special object that wraps a native operating system handle, and it's always guaranteed to be cleaned up properly by the GC system. There's several variations of safe handle that have already been predefined for you within the framework that sort of encompass most of the scenarios that you'll need. And so you saw safe file handle already. That represents a file handle of some kind. But we also have the more generic ones. Safe handle -1 is invalid, and safe handle 0 or -1 is invalid. This just indicates the int pointer handle that's being held onto by the safe handle itself. What value is considered invalid? Is it just -1 or is it 0 and -1? In other words, it has to be a positive value. We also have the safe registry handle. This is used predominantly in Win32 to access the registry. And then we have the safe wait handle that allows us to clean up synchronization primitives that are used in .NET. So here's an example. The way that we implement a safe handle is we derive from one of those safe handle types. In this case, we're using safe handle 0 or -1 is invalid. And notice that we have a constructor that takes our int pointer, so the external client's going to allocate the handle. They're going to be responsible for calling the native API to actually allocate it. And they're going to pass us in the existing handle that we're going to call setHandle on in order to associate with our safe handle type. And then we're going to implement one method on it called releaseHandle. ReleaseHandle is going to be called by the system either as part of a disposal or as part of a finalizer, a critical finalizer in this case, and it's going to ensure that the handle gets released. So notice that we're simply going to call some unsafe native method here to close the handle on our behalf. And this is all the code that we need inside of our safe handle. Then this type here is used by our client in order to sort of control that handle itself. So our client only implements iDisposable, and then the handle takes care of the actual native cleanup. So let's just look at an example of this, of using safe handles in an actual managed application. So for this final demonstration, I want to show you a practical example of a safe handle. So I've created an Xcode project here, which ultimately ends up being an iOS library. And I've got a C++ class that I'm going to use here. So this will just be native C++ or native code generated from C++. And I'm going to export a series of C methods just so I can use pinvoke. And so you can sort of see how I might wrap something that's native from the operating system. And notice that I've got three methods here. Create magic number that returns me a pointer to a magic number. I've got delete magic number that releases that pointer. And then I've got a method to go retrieve the value from the magic number. And the magic number is just 42 because that is the magic number. Now I'm creating a library from this, and then in my Xamarin iOS app, I'm importing that library. So you can see it's right here, libmagicnumbers SDK. And I've wrapped it in an object here that implements Disposable. And you can see sort of the logic that runs here. We create the magic number that returns us an int pointer handle. I can't use magic number star here because that's a C++ object. I don't know anything about it. From C#'s perspective, it's just an opaque handle that I'm going to interact with. You can see I go ahead and dispose that by deleting the magic number. And then I have a finalizer that does that same disposal. So notice here, I am disposing it regardless of whether or not disposing is true or not, because this is a native handle. And so I don't have any code in here that says is disposing and then only do manage stuff versus native stuff. In this case, I'm only holding a native thing, and therefore I'm always going to get rid of it. Then you can see I've got three static externals here that are defined in the class that are essentially my native entry points. One for create magic number, delete magic number, and get value. Every place where we had magic star, the magic pointer, we're using int pointer instead. Now I'm going to use this class for my view controller, so you can see that I'm creating a new magic number here, and then I'm going to set the text of a label to whatever comes back out of that value. So if I run this, this will display two view controllers, or two views. So the very first one will just be a button. So the app comes up and it says, okay, give me a magic number. I click it, and notice I get back 42. And you can see over here that we're getting created a magic number with a hash code, and then I see magic number dispose was called with disposing equal to false. Now what that should tell us is the finalizer got called. So the system didn't dispose it, and I'm not disposing of it anywhere. Notice I'm not calling dispose here, but ultimately what happened is a GC occurred, and as soon as that GC occurred, the finalizer for this magic number got called, and so therefore we freed the handle. Okay. Now, you could totally do it this way. This does work. And conceptually, there's nothing even wrong with this code. In fact, Xamarin Android and Xamarin iOS pretty much use this exact pattern almost everywhere. But we do have the capability of using safe handles. And so I'm going to add in a better magic number. And I'm actually just going to copy the magic number contents from this one. And we'll just rename it here. So we'll call this better magic number. Okay, now, this will be better, and this will be better. Now let's just go through it and see what we can do to fix this up. And this also needs to be better. Okay. Now, the first thing I'm going to do is I'm going to create a safe handle class variation. And so we're going to do just an internal class here to kind of manage this. I'm going to call it magic number safe handle. And I'm going to derive this one from safe handle 0 or -1 is invalid. Remember, this is one of those built-in types that's in the system. Notice that it's telling me that, hey, wait a second, we've got some abstract methods that we don't implement yet. The one that we need here is the release handle. I can use the nice little IDE implementation to say implement that abstract class. Now, once I have that, I'm then going to want to go ahead and hold on to this. And so what we're going to do here is first create a default constructor. And this default constructor is going to pass to the base. And I'm just going to say true that I own the handle with no parameters. This is a requirement of safe handle. This gets called in a couple of the interop scenarios. And so we want to make sure that that's there. Now notice that that is, by the way, internal. It's not marked with any particular, it's private rather. It's not marked with any visibility. So it's just a private constructor. Then let's go ahead and create one that we're actually going to use. So safe handle, let's take as a parameter an int pointer. So we're still going to represent our handle as an int pointer. I'm going to go ahead and pass to the base and say I want to own this handle as well. And then we're going to call setHandle, passing in that handle, right? So this method here is a base class method, and it associates this int pointer with our magic number safe handle. And then in our release handle, this is where we actually want to get rid of this object. And so here, let's just output something to say that we're going to release it. And so we'll say magic number safe handle dot release handle. And we'll go ahead and pass in this, which means we need to override the toString implementation. And then let's go ahead and say delete magic number. We have access to those little DLL imports down there, and we'll pass in that handle. And I'm going to return true, saying that we did get rid of the handle. Then let's override toString. And what we'll do is we'll just go ahead and output the actual handle itself. And so I'm going to say dangerous get handle. It's a method that's on the safe_handle class that allows me to retrieve the underlying int pointer. I'm going to say toString, and let's just cast it to a hexadecimal value. That'll give me the same value that we were using before. Now let's go ahead and modify all these places to use our magic number safe handle. So instead of an int pointer, we're going to use this, and so I'm going to call this safe handle. So here, I'm going to create a new safe handle, magic number safe handle, and I'm going to pass it the int pointer that we were creating originally. And then notice that I'm going to go ahead and say creating better magic, and instead of handle here, we want this to be safe handle. Same thing for dispose. I'm going to go ahead and dispose the safe handle. So we'll go ahead and say, let's get rid of the safe handle itself. And in fact, in this case, I don't even want to do any of this. I just want to do this. I want to say safe handle dispose, right? Since it is disposable in itself, we can just go ahead and dispose it right here. This is all fine, this is all fine, and then the last thing we want to do here is go ahead and use safe handle for this. Now, notice something interesting here. So it's giving me a little bit of an error because this down here is marked as taking an int pointer. So get value, we actually want to change this to be magic number safe handle. So for this final demonstration, I want to show you a practical example of a safe handle. So I've created an Xcode project here, which ultimately ends up being an iOS library. And I've got a C++ class that I'm going to use here. So this will just be native C++ or native code generated from C++. And I'm going to export a series of C methods just so I can use pinvoke. And so you can sort of see how I might wrap something that's native from the operating system. And notice that I've got three methods here. Create magic number that returns me a pointer to a magic number. I've got delete magic number that releases that pointer. And then I've got a method to go retrieve the value from the magic number. And the magic number is just 42 because that is the magic number. Now I'm creating a library from this, and then in my Xamarin iOS app, I'm importing that library. So you can see it's right here, libmagicnumbers SDK. And I've wrapped it in an object here that implements iDisposable. And you can see sort of the logic that runs here. We create the magic number that returns us an int pointer handle. I can't use magic number star here because that's a C++ object. I don't know anything about it. From C#'s perspective, it's just an opaque handle that I'm going to interact with. You can see I go ahead and dispose that by deleting the magic number, and then I have a finalizer that does that same disposal. So notice here, so now let's go back to our view controller and let's actually change this to use our better magic number. And let's run this and see what happens. And we really shouldn't see any major behavioral differences. The difference really is simply in the implementation and the fact that our magic number wrapper no longer needs to implement a finalizer. So I call get magic number, notice that I still get 42, and now I can see that I created my better magic number. Notice it's not been disposed, so no finalizer is being called, dispose isn't being called, but now I can see that I get my magic number safe handle, release handle, against that same handle value. And so really that's the big difference here, is simply that this implementation is safer because I no longer have to deal with a finalizer, and instead I'm deferring or pushing that logic into this little wrapper that the runtime takes care of for me. So the runtime will ensure that this is called. And it does it partially through a finalizer, but it's a special form of finalizer that the system tracks, particularly in .NET. They make a lot of guarantees about this in the desktop .NET variation. In particular, if the app domain is shutting down because of some kind of termination, like a Stack Overflow, they guarantee that these safe handles will get cleaned up. Now, Mono today does not make that guarantee, but .NET does. And so this is, in fact, a much better way to implement your own interop sort of scenarios, and .NET does it this way everywhere. Mono today does not, primarily because this introduces a little bit of overhead compared to an int pointer, simply because these safe handles are reference objects, and so we end up doing more GCs. And on the mobile platform, that has a more significant impact than it does on a desktop platform, where we've got a lot more memory to play with. And so today in Xamarin Android and Xamarin iOS, they don't use safe handles for all their framework objects. Instead, they use the pattern that I showed you initially, where we have a finalizer and we have iDisposable. But for your things, this is definitely recommended. You should definitely consider using safe handles anytime you're doing any sort of interop scenarios where you're calling into the OS and holding onto some kind of handle for that. So now you've seen the process of cleaning up our non-memory based resources. And the way that the system sort of manages this using finalizers and the iDisposable interface, and then finally the dispose pattern, all of those things together. So just in recap, We use finalizers to clean up native operating system resources. We use Disposable to clean up both native and managed resources. And we use the Dispose pattern in order to sort of version our application properly, or at least our types that implement Disposable, so that we can then derive from them and kind of hook into the Dispose pattern itself. So hopefully this has been helpful to you in sort of understanding a little bit more about how the garbage collector works with our non-memory resources in order to kind of clean things up. Again, my name is Mark Smith, and if you have any questions, you can see my email address there on the slide, or you can post into the Xamarin University forums. But I hope this has been helpful, and I hope that you have a great day.